So it's probably time to start. So thank you for coming. It's a pleasure for me to teach during the night. So something new, I must say. And I gave you a kind of outline. And so this outline will be probably for you a kind of a souvenir, maybe also a clock, because if it's too boring, you see that it's progressing, and there is maybe an end at some point. And also you'll see that what I would like to discuss tonight is, as I said initially, wetting and roughness, but I was told to start more or less from scratch. I was told that your backgrounds might be very different, and so the first part is, I must say, embarrassingly naive and simple. It's really simple laws in wetting, but it's very useful for the rest of the talk. So the first half an hour, I'm very afraid that most of you are completely aware of that. I hope that the 75% which come after will be with some aspect at least new for you. So if I had to say something very simple and very general, I would say that wetting phenomena have been studied for very long because they are useful. It's useful to understand how a liquid behaves close to a solid. And so people from companies very early started to think about that. But what is quite new is the understanding or the fact that people realize that if you add roughness, which is very natural because most solids are rough, but also today it's possible to induce a special roughness, and it's mostly what we are going to discuss, then wetting might become even more exciting in the sense that you can generate using let's say structures, textures, properties which you could not without these structures. So it's really not exactly modification of usual laws of wetting because there is some roughness on your solid. It's really trying to induce new properties using something on the solid. And so I'll try, so there are examples which are very famous about that, but I'll try to make a kind of list of exciting problems, and some of them are, I think, really new in the sense that they have been very poorly studied, so I would be, of course, very interested in your reactions. By the way, I guess that most of you work in fields which are somehow related to what we are going to discuss tonight, and I will be very happy to discuss with you if you have the possibility during the meeting here. So the outline is as follows. So this is very dark, but you have the outline in front of you. So first part, simple views on wetting. So really the state of the art, I would say in the late 80s or beginning of the 90s, which are the classical wetting, if you want. And then three parts. One is about super-hydrophilic states. So the fact that with roughness you can induce enhancement of hydrophilicity, which was discussed, but not that much, I must say. And so it's interesting to see the kind of situations that you can generate with hydrophilicity. Then the opposite case, the case when you have both roughness and hydrophobicity. And this is, of course, by far the most famous part. People were very excited about the possibility of generating what we like to call fakir drops. The fact that the drops can be like pearls on solid, and so as a consequence are very, very easily evacuated from this solid and so on. And my last part is a consequence of the third one. It's what I like to call hydrodynamics without contact. The fact that when you generate a very poor wetting, when you are very close to a drying transition, something like that, then you lose the contact between the solid and the liquid, and so the liquids behave very, very differently from what they are used to. And this is a field which is, I think, really opening in the sense that, well, some ideas are here, but there is a lot to do in this field. So it's mainly something where the future is, in my opinion, in this field. I must add that if I had to, this is the axis of time, of course, tonight, but I would say also that this is the axis of excitement. In principle, the longer you stay here, the more excited you might be, because I will be at least, because I think that these problems are more and more interesting. So, wetting, the wetting, classical wetting. So a very, very natural definition, wetting, is what's happening when you have three phases which meet each other. And I would say that the most common case about that is a liquid which is coming on a solid, here water on plastic, with around air. This is air. And so this is the most common situation, but of course you can imagine many situations of this kind: liquid, liquid, air, solid, liquid, liquid, and even in some cases you can reverse the partners and so on, and so have, I don't know, a solid, vapor, liquid, and so on. And so when we look at the final object that we have, we can notice, I would say, two things. The first one is the shape, and the shape at the scale of this drop, which is a millimetric scale, is obviously a portion of a sphere, or a portion of a circle in this case. So we have a spherical cap, and of course people understood very early, about 2 centuries ago, why we had this very pure mathematical shape. But of course, spherical cap is not a shape, it's a family of shapes. And the second parameter that you have very naturally, once you said it's a spherical cap, is the size of the contact between the solid and the liquid. And people who are interested in applications generally are interested in this parameter, because if this quantity is large, it means that the liquid likes the solid, and this can be beneficial. For example, if you think of a paint on a wall, you want really the paint to spread, but in some cases you want to avoid this contact, in particular if this liquid has some chemical action on this solid. Think about water on concrete, for example. This is a very, or even water on glass. And so there are cases where you want to maximize this contact. There are cases where you want to minimize this contact. So these are the two quantities to be defined. So here I said I will be embarrassingly simple, and so this is one point where I'm sorry about that, but the first thing is the shape, and the shape is related to the presence of surface tension at the surface of any liquid. And the reason, as you know, which was more or less understood by different people, but I would say that a very, very brilliant paper on that is due to Thomas Young. The title of the paper is On the Cohesion of Fluids. Thomas Young was interested to understand why fluids are heavy, and he understood that this is related to some attraction between the molecules, which means that molecules close to the surface have a higher energy, which means that the surface itself has a special energy which is proportional to the number of molecules at the surface, that is, to the surface area of my blue line. And the constant of proportionality is called the surface tension of this liquid, and of course it reflects directly the cohesion of my fluid. The more cohesive the fluid, the larger the quantity gamma. And this was understood very early. It's very funny to see that in the very famous book by Goethe at the beginning of the 19th century, 2 years after the paper by Thomas Young, Goethe, in the elective affinities, has a very long paragraph about that, and he says that, of course, mercury has it does not say higher surface tension, but higher cohesion than water, and itself higher cohesion than oil, and so on. So there is a scale of liquid, and there is a scale of gamma. And so as a consequence, the system, if it's a deformable system, which is the case for liquid vapor or liquid-liquid, can choose the surface area which minimizes this quantity. And so this is the reason why you observe spherical shapes very naturally. But this is only for the liquid vapor boundary. However, of course, you can define this kind of quantity for any surface. Each time you have a contrast between two surfaces, you have a corresponding gamma. It can be between solid and liquid, solid and vapor, and liquid and vapor. And wetting phenomena is interesting because you have three of these parameters, because you have three phases, and so you have three kinds of boundaries, which are, in my previous example, solid liquid, solid vapor, and liquid vapor. And so now what we have to understand is the contact between the solid and the liquid, and because we know the shape, and because, of course, we know generally the volume of liquid that we deposited on a given solid, it's equivalent to think in terms of contact angle. And so this, once again, is due to Thomas Young. Thomas Young was the first to calculate the value of this contact angle. He noticed very early that the contact angle is a property which is really local. It does not depend on the size of the system. And so this is a little experiment where you take the same plastic, you put the same liquid, but you vary the volume of liquid. And as you can see, the shape, of course, depends on the volume. When you have a large volume, the shape is flattened by gravity. You lose the spherical shape because gravity acts and makes the liquid flat. But the contact angle in the three cases is the same. So it's fixed at a very, very local scale. And there are many discussions about that. What kind of scale should we define? And if we go at a very small scale, do we still observe the same macroscopic contact angle and so on? It's not something that I shall address tonight, but of course, it's a very, very interesting question, which is interesting statically, but it's also interesting dynamically, of course. If you start to move this liquid, of course, these questions of scales are absolutely crucial. So the way this angle is calculated is very classical. So in case you never saw that, I do it quick. So this is your solid. The liquid is here, and it makes a corner, and I focus just close to the contact line. The contact line is this very special place where you have the three phases, liquid, vapor, solid, and it's a place where the contact angle is somehow decided. And the way to calculate, there are several ways, but one which is very elegant, I think, consists of thinking of the successive little jumps that a drop makes when it contacts a given solid. And you look at the end of this story when you reach the final equilibrium contact angle. And so you consider the last jump. And this jump is made by a quantity which is here, dx. And you calculate the corresponding change of surface energy using the formula, the general formula that each time you have a surface, you have a corresponding surface energy. And so the corresponding variation of surface energy here is written per unit length of the contact line, so per centimeter. And first you create solid-liquid interface. You suppress solid-vapor interface. You do that on a surface area per unit length, which is just dx. And of course, as a drop spreads, you create blue line. So you create a surface here, which is this little segment. And so you have to add here gamma LV, the liquid vapor surface tension, dx cosine theta. And of course, the drop stops when it finds its equilibrium, which means dE is 0, from which you find this wonderful compact formula, which is that the cosine of the angle is a difference between the two solid surface energies divided by the surface energy of the deformable surface. It's a ratio. It must be, because it's a dimensionless quantity which is built with quantities which have dimensions. And each time you have a ratio in physics, it means that you have antagonistic forces. And here it's the case. The force which is at the numerator is the one which spreads or not your drop. And of course, the denominator betrays the fact that when a drop is spreading, its surface tension, liquid vapor, resists any spreading. So this force, of course, opposes the spreading. So it's very natural to find a ratio. When you look at the original paper of Thomas Young, you have no equation of Young. You have nothing like that, of course. This is a modern way of thinking. You have a kind of representation which I think is this one. And this one is very subtle. It's not easy to use generally, but it's so beautiful. There is no calculation, but I cannot resist telling you exactly what's proposed by Thomas Young. So, of course, you have to think of the contact line. And I would like to say that the contact line is a place where each interface stops. You see, for example, if I look at the solid-vapor interface, it stops here, because then it becomes something else, which is a solid-liquid interface. If I look at the solid-liquid interface, it stops here. And the liquid-vapor stops here also. So there is something very particular to the contact line, which is the fact that at this point, the interfaces stop, which means that at this point, forces are acting in such a way, look at this energy, in such a way that each of these surface force tends to minimize the corresponding surface energy. For example, if you look at the solid-vapor interface, it tends to draw the line towards the right here, because if it does so, you suppress surface between solid and vapor. And so this is the way this force, because of course, when you see the dimension of this quantity, you see this is an energy per unit area, but it's also a force per unit length. And so this force tends to act in this direction. Of course, solid-liquid interface acts in the opposite direction, and liquid-vapor interface acts parallel to the surface, which is in this oblique direction. And so when you say a drop is at equilibrium, it stops, it finds its optimum state, it means that these forces have to balance. And of course, if you balance these forces on the horizontal line, you immediately recover Young's equation. It's a very, very elegant way of thinking, but it's very difficult to use when you have a complex surface. You get very easily lost in this force, at least me, in these force balances. But I think it's nice to see it at least once. By the way, if you project on the vertical direction, it seems that something very strange happens. There is apparently no force opposing this one. And so people thought about that in the 90s, I would say. And they realized that this force is existing, this vertical force, and it slightly pinches the solid below. And so if you look carefully at solids which have a very low Young modulus, something like the surface of a yogurt, for example, on which you deposit a drop of water, you can see small deformations which are related to the fact that you have this vertical force which is active and which is resisted by the elasticity of the solid below. So there are limits in this equation which are extremely interesting, both conceptually and for applications. And one is the limit of complete wetting. The fact that in some cases you take a solid, the same plastic, you put a liquid, now it's not water, it's an oil, and you deposit your drops, and they spread very, very, very nicely. And they make a film, and the thickness of this film, of course, can be questioned. The dynamics of spreading can be also discussed. There are many discussions about that. But of course, the question is how can this happen? And if we think of the film, it's something like that. And of course, this film, if it is fed by my pipette, progresses to invade the solid. This is what we saw. And now if I think about Young's construction, it's very clear that at this point, which is the point at which the interfaces stop, it's not exactly a contact line, but it's a termination point of the interfaces. I have my previous forces, but they're acting in a slightly different way because my film is very flat. And I realize that if the solid vapor force is larger than the sum of the two other forces, then indeed the liquid has to spread. And so this is a natural condition for achieving complete spreading. And when I come back to this equation, I realize that it means that the numerator must be larger than the denominator. And of course, this makes sense. I cannot define anymore a cosine if this quantity is larger than unity. Okay? So it's very well connected to Young's equation. A priori, there is no limit for these quantities. They can be anything. And so there might be a possibility such that this quantity is larger than this one. And so it means that the liquid is spreading on this solid. So it means, for example, that the solid must have a very high surface energy, which is the case for glass when you make it. And when you go to in a factory of glass and you look at the glass, it's very fascinating. You can take a drop of water, you put the drop of water on glass, and it spreads very nicely. Something that you never observe on window panes. The reason being that a surface with a very high surface energy is immediately polluted by anything, because anything lowers the surface energy of this solid. And so after typically 5 minutes, it's very, very short in normal air, your glass is not wetted anymore by water. But we guess from this criterion that very generally a solid of very high energy should be wetted by more or less anything, except if this anything has itself a very high surface energy. Of course, if you think of mercury, mercury does not spread on any solid. And the reason is that this quantity is extremely large for mercury, so this cannot be satisfied. Of course, if you have any questions, you please tell me. This can be said in a slightly different fashion, and this way of thinking was proposed by Mahogany, an Italian physicist during the 19th century. He said, well, we have a solid which is dry, and possibly, when the liquid is coming, this solid can become wet, and this means that we change the nature of the surface energy. It was a surface energy of a dry solid, and per unit area, the surface energy is gamma solid vapor. And when if a film has spread on this solid, I have now two interfaces with two corresponding surface energies. And of course, I find the same criterion. If this energy is smaller than this one, it means that it's favorable to spread the liquid on the solid. And of course, I find exactly the same criterion, which is cosine theta larger than unity. There is another way to approach this interesting limit of complete spreading, which consists of coming back to Young's formula. And this is to prepare something we'll see later. If in this formula, I imagine my solid is such that it looks a little bit like the liquid that I'm going to put on this solid. It's liquid-like. So I look at the formula and I find gamma liquid vapor, okay, minus gamma liquid, which is nothing, over gamma liquid vapor. So the ratio which is here tends towards 1. And so this means that the angle becomes 0. And it's a very trivial result in a sense. The fact that if my solid is liquid-like and if I come with the same liquid, of course the liquid will spread on this liquid. If you put a drop of water on water, it will spread on water. But it means that if I find tricks to treat my solid in such a way that it becomes liquid-like, I will go in this interesting direction without having something necessarily chemical. And so this is, of course, a way to say that roughness might help to make a solid liquid-like, as we'll see later. The opposite limit is, of course, very interesting. How to make drops very spherical, like pearls, how to reach very high contact angles. Well, chemically, it's not possible. And there were long debates in the 60s, and I should quote here the name of this man, who wrote quite a famous paper, whose title was The Upper Limit for the Contact Angle. And so it was an empirical paper where he looked at the possible chemistry at the surface of a solid. He made extrapolations. He was a master at that. And he found that very probably it will be impossible to find with water, which is the most natural liquid, solids on which the contact angle is larger than 120 degrees. And so if you develop very sophisticated fluorinated molecules to put on your solids, very sophisticated waxes, you cannot go beyond this limit. And I think this is true. Just chemically, on a flat solid, for which you expect this relationship to be obeyed, more or less, it is true that the largest contact angle are not that large. The largest one should be 180 degrees, and there are 60 degrees which are missing. So really there is some space to fill here. Again, if you come back to Young's formula, you realize that there might be a possibility to go much, much further if you make your solid vapor-like now instead of liquid-like. So if you find a trick to make that the solid somehow resembles vapor, air, then you look at the formula, it's gamma VV, which is 0, minus gamma VL over gamma LV, and so of course this makes -1. And so it means that if your solid is vapor-like, the contact angle should go to 180 degrees. And so what I just said before is the fact that chemically nobody knows how to make a solid vapor-like, but we'll see that with textures, as you probably know, it's possible to approach this limit because it's possible to trap air, and so this is a way to make a solid, of course, vapor-like if this solid is filled with little bubbles of air. There is even one limit where this is completely satisfied, which is the limit of Leidenfrost. So it's a very special one, of course, but it's a very interesting one. You take a solid and you bring this solid at a temperature which is much larger than the boiling point of the liquid. So typically steel or copper at a temperature of, let's say, 300 degrees. And you deposit a drop of water on this solid, and you see a perfect non-wetting. You see something even better, which was discovered very long ago by this German physician in Duisburg. He put a candle behind, and he could see very clearly the light passing below the drop. And so he understood that these drops are not contacting anymore the solid. So indeed, if they are not contacting the solid, there is no contact angle, there is no contact. They are levitating on a little cushion of vapor that they feed constantly because the solid is so hot. It's funny because when you look at these drops, there is no boiling inside. This is remarkable, of course. The solid is very hot. The liquid is at the boiling point, but you do not observe any boiling because there is no possibility of nucleation because there is no contact. You also notice that at the scale of 1 millimeter, which is here, the thickness of the vapor film is typically the thickness of a hair, so 100 micrometers. So it is visible with the naked eye. And so we can understand that Leidenfrost, who did this very careful experiment, could indeed clearly understand the origin of this phenomenon. And as you can see, this phenomenon is captured by Young's equation because it's a case where the solid became a vapor, in which case we find cosine is -1. And so, of course, this is for people interested in this field, this is the ultimate goal. We would like, this is a Graal, we would like to approach this situation. And the question is, if we approach it, do we get properties which are comparable to the properties of Leidenfrost drops? Probably you saw drops of liquid nitrogen on the floor. They are so quick, they are so mobile. And so it's interesting to try to guess if we are not exactly at 180 degrees, but let's say at 170, is it extremely different or is it comparable? And this is a question which is, I think, very interesting because there are probably many answers to this question. We'll come back to it later. So these are, I would say, the general laws of wetting. And I would like to add a few complements, which I think you know quite well, which is the fact that on real surfaces, real meaning that surfaces where you find many defects, this beautiful law is generally not obeyed exactly or must be discussed carefully, as proved by this very naive experiment where you have a solid and you tilt it and you deposit your drops. So this is the first one that you deposit. You make one which is slightly larger. So this is my second drop. And you see in both cases, they stick to the solid. Okay? Both these drops remain immobile despite the slope. And so it means that the contact angle is not unique. Because if it were unique, if you had one given theta here and here, of course the drop should run the slope. The reason being that you do not affect any of the surface energy when you follow the slope, and you lower your gravitational energy. Of course, if you make the drop larger, at a scale where gravity deforms it, then of course gravity becomes larger than surface forces, and so you observe very naturally a movement. Something that we all know from window panes. Again, when it's raining, we see the little ones are stuck, the big ones go quite straight. If you take a picture of these stuck drops, you see that indeed they are very asymmetric. Okay? There is a large angle at the front, a smaller angle at the trailing edge, and you can define a difference between both angles, delta theta, which can be very large. In this case, you see 90 degrees, 30 degrees, the difference is typically 60 degrees. So it means that if I had to define the contact angle for this drop, I would say, well, it's 60 plus minus 30, something like that. So it's not a small variation. It's not saying, well, this is nearly satisfied. In this case, it's very far from that, you see. And so people were extremely interested in the origin of this quantity, consequences of the existence of the so-called hysteresis of the contact angle, which is the phenomenon which is here, and calculating possibly this quantity. And so, well, this was more or less successful. So, consequences first. It's interesting, once you understand that these drops are asymmetric, it's very clear that they must stick. Why? Because you have a very famous law. Young's law is famous, and the second big law in capillarity is Laplace law. The fact that when you have an interface which is curved and you cross this interface, there is a jump of pressure. And so here, the curvature is not homogeneous, is not constant, which means that the pressure is not constant. When you cross the interface here, there is a large jump of pressure because the curvature is high. When you cross the interface here, there is a smaller jump of pressure. So there is a pressure force which is acting that way. And so, of course, this is the reason why the drop sticks. This force balances gravity. And so when you say that, you can somehow evaluate this force, you can calculate it, and so you can build a kind of phase diagram about the mobility of your drop. So you fix the angle of your solid. In this case, it's a vertical solid, so maximum angle. You fix the size of the drop, the size of 1 millimeter, which is a very typical raindrop. And you look for given delta theta, which is somehow a characteristic of your solid and your liquid, and the mean contact angle theta. You look at the possibility of satisfying or not a balance between this sticking force and gravity. And what you find is something where the majority, the vast majority of the diagram is occupied by the sticking phase. So your drop sticks, and so this is, of course, a very common observation. If I have contact angles between, let's say, 20 and 100 degrees, which are very typical values, if I want my drop to slide or to follow the slope, which in this case is 90 degrees, it's a maximum one, the contact angle hysteresis delta theta must be smaller than a few degrees. So it means that I have to elaborate a solid which is absolutely perfect chemically and physically, because the origin of delta theta is in the defect of the solid. And so this is something which is maybe feasible, but as I said for glass, after a few minutes, there are some contaminants which are coming and you lose this ideality. So if you are interested in solving this question practically, it's impossible to solve this question like this. Okay? You cannot achieve a solid with a permanent delta theta which would be so low. But we'll see later a trick which is, however, makes this region relevant. So you see that there is a second solution which I think justifies the fact that so many people are interested in super hydrophobic surfaces, which is the fact that above something like 160 degrees, of course this value depends a little bit on what you choose here, the line which was there becomes more or less vertical, which means that even if delta theta is quite large, in this region, which is very thin, the drop should be mobile. And the reason is very obvious. When you calculate this sticking force, you have to integrate on the contour of the drop. And so because in this region the drop becomes nearly spherical, it hardly contacts the solid, and so the force vanishes even if delta theta is not negligible. So there is something very clear here, which is that if we are able to make contact angles in this small region, the mobility should be much, much higher than usually. And so this is, it's a very stupid expression, but it's a kind of static mobility, the fact that the drop starts to move. But then what is much more interesting is the dynamic mobility, the fact that if it moves, it will be much weaker than usually. So it's not only preventing the sticking, it's also the intrinsic dynamical properties that you can have later, which we'll discuss a little bit in about 1 hour. A second consequence of the existence of contact angle hysteresis is, so this variation of a contact angle, is the so-called Coffeestained effect, something which was studied in the years 2000, in particular by the Chicago group around Tom Whitten and Sidney Nagel. So they took pictures of a drop of coffee as it evaporates. So it's an experiment for, let's say, a lazy PhD student because it's very, very slow, and so it takes typically 1 day, and you take 1 picture per, I don't know, half an hour, and then you make a movie of that. And from the top, at the beginning, of course, you see that it's darker at the center than at the periphery because of the shape of the drop. And so it means that you have more particles of coffee at the center than at the periphery. And if you look as a function of time at this shape, well, it's clear that you have a displacement of matter, and at the end, you have a kind of stain, and it's something that you probably observed. It's very, very common. And also, which is very remarkable in this experiment, this line never moved. It remained pinned from the beginning to the end. And of course, if the drop were satisfying this equation, so if you had a drop like this and you evaporate this drop, it should make that, to keep the contact angle constant. So the first effect which is there is related to the fact that you start with a given contact angle, and because you have a possibility of having this contact angle flexible, you have this delta theta, then you can pin the line here, and at the same time, something else, of course, occurs, which is the fact that matter is transported from the center to the border. Why? Well, because close to the contact line, evaporation becomes somehow pathologic. It's a region which is with a very high ratio between surface and volume, and so you have to transport matter to feed this region. There is a divergence of the evaporation at this point. And so the solid is transported, but because you transport the solid, you build around the contact line a kind of porous medium, and so you amplify the contact angle hysteresis in this case, because you had a few defects at the beginning, but then you have many, many defects because you have all these little particles that you put at the contact line, and so the pinning, which was maybe quite strong at the beginning, becomes intense. And so this is the reason why until the end, until the drop is completely flat, because of course at the end it's completely flat, it remains pinned by the contact line.
Sorry?
Yeah?
So did I understand that right, that evaporation diverges at the contact line?
Yeah.
Okay.
Yeah. So this is the proposition of Tom Whitten, and they did calculations which are, and they also deduce from that the typical velocity at which particles are transported, and they could prove that it was in fair agreement with the experiments, where you have here fluorescent particles, and you look at these particles under a microscope, and you clearly see this radial transport of particles towards the contact line. Of course, these questions of pinning are absolutely crucial if you want to understand the contact angle hysteresis, this variation of contact angle. And if you think of a chemical defect, so you have a solid which is flat, but the chemistry changes at some point, and so the contact angle would be θ1 here and θ2 there. And of course, at the border between the two regions, you have the possibility of having a flexible contact angle, any value between θ1 and θ2. So in this macroscopic example, it's very clear that a macroscopic defect can generate a fluctuation of the contact angle, And the interval between these values can be as large as you want because it only depends on the values of θ1 and θ2. Same thing with a physical defect. This is a physical defect where you have a kink on a solid. You can imagine, for example, a groove on a solid like this. You don't see this groove. It's at a scale of, let's say, 1 micrometer. But when you put a liquid on it, you always think that everything is horizontal, and you can make a mistake, if I dare say, when you measure the contact angle, because on the left, you observe a contact angle which is θ1. On the right, it's also θ1, but on a slope which is phi. And so, as you can guess, when your contact line is going to the tip here, you have any values between the angle θ1 and the angle which is there with respect to the horizontal, which is pi minus phi plus θ1. And so this can be also arbitrarily large. For example, if you think of filling and even overfilling a glass of water, we all know that when we fill a glass of water, the apparent contact angle can be 90 degrees. It can be even 180 degrees. And for a glass of water, the top of a glass of water, phi is 0 because you have the solid, the wall of the glass which does that. So phi is 0. And if θ1 is 0, you see that at the top, the angle can be between 0 and pi minus 0 plus 0, which is exactly what we observe when we overfill a glass of water. So all of that is very important because it says that, well, pinning is something which occurs very naturally on defects, first thing. And second thing, if we have many defects, the line will find a way to accommodate to these many defects, and then the difficulty becomes terrible. And many people try to solve the following question. If I have a map of a given solid, and I know the strength of the defects, what is the contact angle hysteresis which comes from that? There is no real answer to the many defects problem. A single one, it's very clear. Many defects remains for the moment not really solved. There are a few cases where people found solutions. In particular, there is a very famous one proposed by Dejeune in the late 80s, but it corresponds to a case where the defects are very dilute and very strong, and it's quite far from the reality generally. So it's very difficult to use practically these results. But as you can see, there is finally no contradiction between this ideal law and the fact that we have pinning, for example. You see that locally, I always satisfy my law. And so it's something that we have to keep in mind. The fact that this law is completely local means that there is always a scale where it must be obeyed. And it's something which will be useful slightly later. So this was a very long, a bit long introduction, and I would like to discuss now this quite short paragraph chapter on superhydrophilic states. So now I would like to change really the point of view. So I was saying I consider very ideal solids. Okay, I have classical laws. Now I say solids are not so ideal, so I have some defects, and I try to treat these defects. It's not very easy, as I said. But now I would like to say something different, which is to say I would like to place on a solid very well-defined defects and to try to induce new properties. So this is a picture. We have a solid, and we decorate this solid with some pattern, some structures, at a scale which is clearly above the size of the molecule, but much smaller than the size of the drops which are coming. So if you think of rain, of water, this is typically 1 millimeter, and so this can be typically 10 micrometers. But you have, of course, possibility of changing the scale, and it's something that we'll also discuss later. As you probably know, people from the microelectronics community learned how to build very sophisticated structures of this kind. And so we'll see later examples which are indeed very beautiful. So what could happen? The people who probably really raise the question the first in a very convincing way were the people from the Kao Corporation in Japan in the late 90s. If I had to say what was the main contributions which decided that this field would become very exciting, for me, there is absolutely no doubt that the papers by the Shibuishi, Honda, and so on group are absolutely to be quoted. What they did is a very simple experiment where they took a solid and they textured this solid and they compared the contact angle on this solid when it is flat. So it must be something like a Young contact angle, and so I call it theta. And you take the same chemistry, but you change the texture, you put a texture, so it becomes something like that, let's say. And you deposit the same liquid on this solid. You do not see the texture, so for you everything is horizontal, the scale is too small, and you measure a new angle, which is of course something like an apparent contact angle. You do not know exactly the detail here. And what they did is to compare theta star and theta. And the way they did that is to take two solids of this kind and to put a series of liquids. Okay? And so if you take a series of liquid, you vary theta, and for each theta you can measure theta star. And so it means that they compare the typical wetting as a function of the roughness of a solid. And they find something which is very important, the fact that when you add some roughness on a solid, generally you change dramatically the typical contact angle that you observe. So they plot cosine theta star as a function of cosine theta, and if the roughness had no influence, you would have theta star equal theta, which is the red line. Okay? And the red line is obeyed by one poor little point. What you find is that on the hydrophilic part, so the hydrophilic part is this one, the cosine is positive, and if the cosine is positive, it means that the contact angle is smaller than 90 degrees. Then you find that theta star is always smaller than theta, so a hydrophilic solid becomes more hydrophilic. Conversely, if theta is larger than 90 degrees, you find that theta star is even much larger than theta, which is a hydrophobic case. So we focus now in the hydrophilic part, and of course we would like to understand what's going on here, and you can do at least, and when I say at least, there are people who are discussing what could be the other possibilities, but generally it's reasonable to say that there are three main possibilities when you deposit your solid, your liquid. The liquid can somehow follow the accidents of the solid, or maybe it could stand at the top of the solid, or maybe it could leak in the solid. So the liquid could think, oh, I am on a kind of porous medium, so I start to invade this porous medium. It's a very special porous medium, of course, because it's a 2D porous medium, but however, you can treat this solid as a kind of porous medium. And so in each case, the drop is in contact with something which is very different. In the first case, it's in contact with a rough solid. In the second case, it's in contact with the tops of the solid. And here, it's in contact with something which is filled with the same liquid. And of course, you remember I told you that if you make the solid vapor or air-like, you have something that you expect. And so this solid is air-like now. If the solid is liquid-like, you expect something else, and this solid is a bit liquid-like, and so you understand that using roughness indeed helps you to go in these interesting limits. So the man who developed the first model about that, he's quite famous. His name is Wenzel, and Wenzel did a variation on this equation which is there. Wenzel started from this picture, but on a rough solid. And on a rough solid, you must introduce at least one parameter, which is the so-called roughness factor. And the definition of the roughness factor is incredibly simple. When you look at the solid, you don't see anything special, so you think the surface area of this solid is this width times this length. But of course, the real surface area, if you want to measure it, you have to take into account these valleys, these mounts, and so on. And so if you divide the real one by the apparent one, you find a number, which by definition is larger than unity, and this is called the roughness factor. So if now you have here a rough solid instead of a flat one, you can define its roughness factor little r, and if you think exactly in the same way, you say I put my drop, it makes little jumps and it stops when it finds its equilibrium position. Well, I can exactly follow the same line, except that the apparent jump of dx is in reality r dx, and except the fact that the contact angle now is not theta but theta star. And if at equilibrium dE is 0, I find something which is very, very simple, which is that cosine theta star is r cosine theta. And so apparently, in one very compact formula, everything is understood. When theta is smaller than 90 degrees, this cosine is positive. I multiply by a number which is larger than unity. So I make this number larger, so it means that theta star is smaller. When I am in the hydrophobic part, this is a negative number. I multiply by a number which is larger than unity. I make this number more negative, and so theta star is larger than theta. So Wenzel predicts that hydrophobicity is enhanced by roughness, by hydrophilicity is enhanced by roughness, and this looks in qualitative agreement with what we said previously. And actually, this is the way the people from the Kao Corporation interpreted the results they had. However, it's very clear that it's not true. When you look at this relationship, it should be a linear relationship where the slope is r, the roughness factor, which, by the way, is something amazing. It means that this little parameter, which should be extremely difficult to measure, imagine that you are asked to measure the roughness of a solid using sophisticated techniques of imaging and so on, and then reconstruction, 3D and so on. But here you learn that with 2 drops, you are able to extract this quantity, so it's really wonderful, but it works very rarely. If you are very optimistic, you might say that I can follow with my little arrow here, from here to here, which is slightly more than 2 points, but not that much. You have a straight line. And when you measure this straight line, in the case of this experiment, you find 3 point something. And when you try to extract the roughness factor from the pitches of the samples that they made, you find 3 point something. So it means that very probably Wenzel relationship is obeyed here. But this relationship also predicts things which are not observed. In particular, remember, I told you if cosine here becomes larger than unity, it means that your liquid is spreading on the solid, which is a very, very important and useful possibility. Here, it could be the same. If you have a cosine which is, I don't know, let's say 0.5, if I have a surface whose roughness is 3, it makes 1.5, and so I predict that the cosine being larger than unity, it should spread. But this is not obeyed. You see, this red line does not cross here the line 1. Instead, there is a change of a new regime where it somehow saturates, and very, very slowly it tends to the complete wetting, which is reached only here. So it means that you cannot induce complete wetting by roughness. You can enhance hydrophilicity, but not create a new regime of filmification, something like that. So of course, it's something which is quite important practically, but also because it tells that this relationship seems to be obeyed at the very beginning, but not later. On the hydrophobic side, it seems that it's never obeyed. There are very, very little data because I told you that the contact angle cannot be very large. Theta cannot be very large, and so you have no data in all this region. But it seems that you observe immediately a kind of discontinuity, and we'll come back later on that. So what does it mean? What's happening between the red line, which is here, and the blue line, which is there? Well, you probably remember that we had a few pictures. So this was the Wenzel picture, the picture where the liquid follows the accidents of the solid, in which case I can write what I did here. But there is another possibility, I said, which is the fact that the liquid might choose to invade the little cavities on the solid. And so the question then becomes, why should a liquid, do something like that? Okay? And I think it's quite an interesting question. So this is a corresponding picture. You have a liquid, so maybe there is a big drop here. We do not see this drop. And you assume that this liquid has chosen to invade the little cavities. And then you say it's here, and it progresses by an amount which is dx. And the question is it favorable or not? And so for that, you have to write an energy balance, which is the following. There is a chain of surface energy here, which is related, when you make this little jump, to the fact that you create new surface between solid and liquid. Okay, so you have the corresponding surface energy, which is gamma SL. You suppress surface between solid and vapor. It was dry, it's not dry anymore. And you do that, this is the only subtle part, you do that on a surface area which is proportional to the roughness factor, because of course it's proportional to the surface that you invade, which is proportional itself to R, minus something, because you assume that the top of the post remain dry here. Why? Because the only possibility for having a film which propagates also on the top of the mountains is to have a complete wetting. Okay? And of course, if you have a complete wetting, the liquid will invade everything. It's a question where we know already what will happen. It will invade everything, whatever the roughness. And so here we have to put minus the total roughness minus the fraction f which remains above the sea. So when you look at that from the top, you see a kind of sea which is progressing, and you see islands, which are the dry parts. And the proportion of dry parts, which is here on this very simple design, just the tops of the design, it's the proportion f. And so this is times dx, and again it's written per centimeter of line perpendicular to the picture. So if it were classical wicking, if it were like in a classical three-dimensional porous medium, this would be the final balance. And so because R is larger than unity and because F is smaller than unity, this is positive. And so we would have that dE is negative. So the liquid is invading the porous medium if this quantity is negative, which means when I go here that cosine is positive. And so it means theta smaller than 90 degrees. So this is the usual criterion for wicking. If a liquid is so-called hydrophilic, if the contact angle is smaller than 90 degrees, then it should propagate in a sponge. Okay? But what is original in this situation is the fact that, contrasting with usual porous media, when the liquid is progressing, you create new surfaces between liquid and vapor. And this is not the case when a liquid progresses in a tube. When it progresses in a tube, you have a meniscus, but this meniscus is always the same. Okay, so the meniscus does not enter in the energy balance. Here, you have to create new pieces between liquid and vapor. And so you have a sign plus here, which makes that this negative thing is not obvious, plus gamma LV, because it's liquid-vapor interface, times 1 minus F, which is the surface area which is covered by the sea, what I call the sea, times dx. And so you see that when I use Young's relationship, which is there, and I express the fact that this is minus gamma LV cosine theta, I find that this criterion, to say that dE is negative, the energy is lowered when the liquid progresses, is equivalent to cosine theta larger than something, and this something is 1 minus F over r minus f. And I like a lot this expression because f by definition is a number smaller than unity. R by definition is a number larger than unity. And so this is a number which is between 0 and 1. And so I can say that it's the cosine of something. You see? It's an artificial angle which is given by the particular design of my solid. For example, if you think of these little pillars and you make these pillars the same but higher and higher, you do not change f, but you change r. And so you see that this angle should be affected. And so what we find is the fact that the liquid will go inside the cavities provided that the chemical contact angle, the one given by the choice of the liquid and the choice of the material which makes the solid, is smaller than this critical angle, which is only a function of the design of my solid. So it's very nice. It means that I can decide which liquid will go inside the cavities and which will not. I can decide by tuning the design, for example, or by changing the liquid. But there is a complete decoupling between the chemistry and the physics, which are in these two angles. We can see very simple limits here. For example, if you have a very, very rough solid, so you imagine that the pillars are extremely long, and so it becomes a quasi three-dimensional porous medium, then R becomes nearly infinite, and if R becomes nearly infinite, as you can see, theta c becomes 90 degrees. So it's exactly what I said previously, the fact that in a classical porous medium, the criterion for wicking is just hydrophilicity. If the contact angle is smaller than 90 degrees, then the liquid will propagate inside this porous medium. If now my pillars becomes extremely thin, the opposite limit, so it's nearly flat, so it means that R tends towards 1, and then this quantity becomes 1, and so theta c becomes 0. And so here I recover something which is quite trivial, which is the fact that a liquid will spread on a solid if the contact angle vanishes. The contact angle has to be smaller than something which is close to 0. Okay? So this formula captures everything between classical spreading and classical wicking. You see, it includes these very well-known limits, which I showed at the beginning, but it creates this intermediate domain where you have these, all these little cavities. So first, does it exist? The answer is yes. So this is a top view of a solid which is decorated with little posts where this criterion is satisfied. Okay? And when you take a top view of a drop which is deposited on this solid, you find something like a fried egg. You see? You have the yellow part at the center, and you have the white part here. And this tells you that you have a coexistence between a drop, a big one, which is at the scale of 1 millimeter, and a film which is propagating inside the pillars. So the fact that you have liquid which is propagating inside the pillars does not mean that you are in a complete wetting situation. It means that exactly like in my little naive picture, here, you can have the coexistence between these two states, which is something not so trivial. And of course, if you have this coexistence, you might be interested in understanding what is the contact angle which is there. Okay? And so this is a kind of exercise that you can do. It's quite an easy exercise when you understood clearly what we did here. Because you can do exactly the same kind of argument. You can say, well, my liquid, which is there, my drop, is progressing on both a solid and a liquid, because there was this kind of leakage which we described. And so it makes little jumps like this, and I can look at the difference of energy between these two situations. And when this difference of energy is 0, it means that the equilibrium is reached, from which we can deduce the contact angle made by this drop on the same liquid plus the fraction f of solid. And so, of course, very logically, we find that this contact angle is not so far from 1, or the cosine is not so far from 1, because, of course, this liquid sits on itself, which means that it should be a very super-hydrophilic situation, but it's never 1. There is a minus something which is strictly positive, and this something is, of course, proportional to the quantity of solid which is still below the liquid. And of course, you can understand this formula as a kind of average between what would happen just on the liquid, in which case you would find 1, the liquid on itself would spread, but there is this correction which is due to the fact that there is still some residual solid below, and so you would never reach exactly 1. And so when we come back to this beautiful law, which is this blue law, it's exactly what is described. It's a linear law, and you never reach 1 except when theta itself is 0. And of course, when theta itself is 0, if the liquid spreads on this solid, the fact that you make roughness does not change anything, it will still spread. And indeed, if you make 0 here, this is 0 and this is 1. Okay? So I would like to finish this little chapter by trying to show you somehow new properties. What can you do with this super-hydrophilic regime? So because it's in the case you satisfy this criterion, it's favorable to fill the little cavities, which means that at the scale of, let's say, 10 micrometers, if you put such a solid in contact with a bath of liquid, satisfying this criterion, then the liquid should invade this solid. And there are interesting questions, such as what is the dynamics of that and so on. But for me, the most interesting question is the fact that once you have filled the little cavities, you have a solid which is very special because it's filled with liquid. If you tilt it, this liquid will not move because at the scale of the texture, gravity does not matter. Surface forces are much, much larger. When you are below the millimetric scale, surface forces dominate gravity. And so you have a very special solid because it's hemi-solid, hemi-liquid. This little phenomenon, my colleague Steve Garoff from Pittsburgh likes to call it hemi-wicking because it's like a 3D wicking, but it's hemi in the sense that there is also an interface with vapor here. And so you can think of using this interface. And I would like to show you an example of that. So this is a solid. It's a top view of a solid that you placed in contact with oil. This solid is decorated with a little texture. You cannot see it. It's at a very small scale. And since this criterion is fulfilled, oil chose to invade the little cavities. And so you have this solid filled with liquid. And now you place little particles on this solid, of a solid filled with liquid, with oil, and then you add a drop of water, okay? And you tilt slightly your solid. When you do that, there is a very beautiful self-cleaning effect, which is related to the fact, mainly to the fact that this drop of water, which would have been stuck in a classical situation, because it's a millimetric drop, here, being on a liquid, will run very, very easily. So this surface can be extremely slippery. In a sense, it's very trivial. It's slippery because it's made of oil. And so we know that if there is oil on the ground, we slip easily. Same thing here. You suppress the possibility of pinning for your liquid. And so it's one case where you suppress contact angle hysteresis because you are mainly on a liquid. Or there is a very small residual contact angle hysteresis, but nothing to do with usual situation. Remember, I told you at the beginning, it's very difficult to make contact angle hysteresis smaller than a few degrees. In this case, it was not possible to measure this quantity because it was too small, because it was mainly on a liquid. And because this liquid this oil is trapped in the cavities, even if the drop is moving, the oil remains in the cavities. So it means that if a second drop is coming, you will still have this slippery effect. So this is one case where you generate a very bizarre solid, which is liquid at the surface, and as a consequence, which is extremely slippery. Another way to see the same thing is to look at the Coffeestained effect on this solid. So if you take it dry, and you come after, I said 1 day, you see the classical Coffeestained effect. And in this experiment, the same drops of coffee were deposited, the same ones, so the size was this one, on one part which was without oil, and one part with the oil inside the little cavities. And because in this case it's completely slippery, as the coffee evaporates, instead of being pinned, very classically, I should say, but this is very unusual, the line recedes as a function of time, and so at the very end you have only the packed population of particles of coffee. And so you make a stain which has nothing to do, it's homogeneous first, and the size, of course, has nothing to do with the size of the classical coffee stain. So it's another proof that you can generate highly slippery surfaces in this case. So it's one first example where you see that indeed you can generate original properties using texture or roughness at a solid surface. The final one I would like to discuss is hydrodynamics, the fact that you can use textures to modify quite deeply, I would say, the hydrodynamics at interfaces. And I would like to take as an example a very classical question of interfacial hydrodynamics, which is the drainage of a film. So you paint a vertical wall and you look at the way the paint thins as a function of time. So this particular paint does not dry, okay, so it's a pure liquid, a layer of oil, and you look at the variation of the thickness as a function of time. When you do the experiment on a flat solid, you find a law which is known as the Reynolds law, which is first the thickness remains constant for a few seconds in this case, and then in a log-log plot it decreases very regularly following a very nice scaling law, 1 over square root of time. So if you want to see where this comes from, there is a very nice little scaling argument about that. So you have your solid, it's vertical, you have the layer of liquid, so it's like this. The thickness is h, and of course it flows because of gravity. This is thin, you see, typical scale, let's in this case 40 micrometers. For a paint, let's say 200 micrometers, so it's very thin films compared to the size of the wall. And so very naturally, you balance, to describe the dynamics of this drainage, you balance gravity, the driving force, with viscous forces. So what we know from Navier-Stokes equation is the fact that viscous forces are the Laplacian of the velocity times the viscosity. So viscosity is eta, and Laplacian of the velocity is this unknown velocity at which it falls down, divided by the size on which the velocity varies, and this size is the thickness, because I have a no-slip condition here, and so close to the solid, the liquid does not move, and if you go further and further, it moves quicker and quicker, and so there are gradients of velocity in this direction. And so it's a square, because it's a Laplacian of the velocity, and this is something that you have to balance with the force per unit volume, which is a weight per unit volume, which is density times g. And so this tells you what is a typical velocity, but the difficulty here is that h is not known because it's a varying function of time, of course, but also an x, which is there. After a while, the film has some profile, and the way to guess what it is, this profile, consists of noticing that there is no characteristic scale on the direction x, which is the direction of the velocity. So v can be written as x over time. And so now if you inject this very simple relationship in this one, you find that the thickness of the film is eta x over rho gt to the 1/2. And if you look at the thickness of your film at a given position, which is exactly what is done in such an experiment, you find that indeed it should vary as the inverse of the square root of time. Okay? So it's a nice scaling law where you recover in 2 lines this famous behavior. So this is the classical, one classical law in interfacial hydrodynamics. So the question is, how do you modify this law if you have a solid which is rough or textured? And we are clearly in the hydrophilic case where your liquid is following this solid. And so this is a very recent experiment. I'm very, very glad to show the first experiment I ever showed in 2011, which is due to Jacopo Severe, and he looked at the drainage on a solid which is decorated by little pillars or little wells. He did different kinds of structures at a solid surface. And he followed the thickness of the film, but here be careful about the definition of what I call the thickness of the film. The thickness of the film is a thickness above the textures. Why? Because at the end of the experiment, remember, the textures remain filled by the liquid. And so the final thickness is, in this definition, is 0. Okay? But the actual final thickness is the size of the cavities. Okay? So it depends, of course, on the definition you give. But here, I choose as a definition of the thickness of the film which is flowing, because I can say the film which is inside the cavities does not really flow. What is very interesting, of course, is the fact that the liquid which is here and the liquid which is there are the same. And they are interacting. The fact that the film is flowing induces some movement inside the pillars, inside the cavities. But at the end, this remains filled by the liquid. When you look at the result, it's completely different. You see that the law for h as a function of time, it looks more or less similar in the sense that it starts with a plateau and then it decreases. This is very natural. This flows due to gravity. But the slope which is there is not minus 0.5, it's minus 1. And this is a very, very interesting law because it's a law when you have slip. If you have slip, which means that if the boundary condition at the frontier between your liquid and below, and here below is this, because it's a boundary condition between the liquid and itself in 2 states, one is free to flow, one is trapped, but it's the same liquid, you have the possibility of generating slip at this boundary condition. And the definition of slip is the following one. When you have a solid like this, if you have slip, if this solid is flowing above, so this is the velocity profile, it means that at the solid or at the boundary there is still some velocity, and then you take the tangent here and you extrapolate until you find 0, and you call this length the slip length. And this is a usual way to quantify the intensity of the slip when you have slip at an interface. A very nice thing about this little definition is that you can show, so it's a kind of exercise, you can try it, it's interesting to do. You can show that in this case, it does not change this law, of course, because it's still moving vertically. Of course, gravity is still the driving force, but here, instead of h squared, you have h lambda. And so, as a very quick, immediate consequence, you see that if I replace here, I find that h now is eta x over rho g lambda t. And so this modifies very dramatically the law of drainage, you see. First, it's 1 over t instead of being 1 over square root of t. And second, the profile is not the same. Here it was a parabolic profile, you see, the film. After a while, the film is like this, while here it's a triangular profile. So it means that you have a film which is completely different. And so all of that means something which for me is very new. Maybe some of you have thought of that, I don't know. But what is very new for me and really exciting is the fact that you are defining a new kind of hydrodynamics here. Using the textures, you modify the boundary conditions, and you modify it very, very brutally in a very essential way. And as a consequence, you can tune completely the flows that you generate. And these flows generally are very, I would say, very robust. And suddenly, you have a possibility of making a new kinds of flow. So this is my final point for this first hour. I was slightly longer. I'm sorry about that, but I will be slightly shorter in the second hour, I promise. And of course, I will be happy to answer questions if there are any. But you deserve the pause.
What kind of technique do you measure the film thickness smaller than a micrometer?
Sorry?
What technique do you use, or do they use to measure the film thickness smaller than a micrometer?
Your question is about the measurement here.
Yeah.
How is it measured? Yeah, so these measurements are made by reflectometry, and this is a mirror, okay? And because the textures are very dilute, you do not affect the reflectometric measurement by the presence of these textures. And so, as you probably know, you can go at the typical scale of the wavelengths of light with this technique. And so this is why there are no data here, because then there is no more any signal. The typical range of accessible thickness here is 0.1 micrometer to, let's say, 30, 40 micrometers, which is the top, more or less. So here you use the whole range of possibilities of your technique in this case, which is nice because you want to test a scaling law, and so you need orders of magnitude. So it's late, so coffee break, okay?